In this section, we're going to study the idea of using stoichiometry, that is weight relations, for compounds and their formulas. And it's the most useful thing we've used to date in this course. In later sections of this chapter, we'll look at the idea of using weight relations, stoichiometry, and chemical reactions. So we're going to do compounds first, then chemical reactions. So section 3.2 is about compounds. We have 5 different things we'll study here. We'll study element composition, which is essentially what are the elemental constituents of a particular compound. We'll look at percent composition from formulas, that's weight percent. We'll look at determining empirical formulas. How do you figure out an empirical formula? We'll determine how you do that. We'll also look at how you determine a molecular formula, and we'll differentiate the two of those as we go along. And finally, we'll look at a special class of compounds called hydrated compounds, compounds that contain embedded water molecules as part of the compound, as opposed to being wet. Okay, so let's look at element composition first. It's actually a relatively simple idea. The idea is if you have a known sample with a known mass, and you know the formula, what are the amounts of each element present? And so the first step is to take your grams of compound and convert that to moles of compound, and we just did that in the last section, so we're not going to do that here. We're going to show the new stuff. So new stuff would be, if you have a sample that's 2.5 moles of this compound here, which is acetic acid, by the way, which is the acid that's in vinegar, what are the amounts of each element present? The term amount stands for units of moles. So you're really looking for how many moles of that. If it was looking for mass, it would have said what mass, or said what's the mass of each element present. And so it's pretty easy. What you do is you take the formula and say you have 2.5 moles of CH3CO2H, and you know that from that you have 2 moles of carbon per 1 mole of that compound, CH3CO2H. And you know that because there are 2 carbons in the compound. And so therefore you have 5.00 moles of carbon. And so that's the element composition for that sample for carbon. The same thing happens for hydrogen. And so this is so easy that lots of times you can just do it in your head. So for oxygen, let's do oxygen first and then hydrogen. There are 2 oxygen atoms in your compound. So 2.5 moles of your compound means that there's 5.00 moles of oxygen atoms. And that's because there are 2 oxygens for each mole of compound. There's 2.5 moles of compound, so it's twice as much. For hydrogen, let's go back and do that one the official way. You have 2.5 moles of CH3CO2H times, you have to think about how many hydrogens there are in the compound. There are 3 in this part of the compound and 1 there. So there's 4 moles of hydrogen for 1 mole of your compound CH3CO2H, which means you have 10 moles of hydrogen. And that's it. That's the element composition. Just that easy. Next, we're going to look at percent composition. And when we talk about percent composition, what we really mean is the weight percent composition. And by that, what we really mean is the mass percent. But nobody actually says mass percent. Everybody says weight percent. So what's the percent by mass of a particular element within a compound? And the idea here is that the compound is formed from 2 or more elements in a set ratio of atoms. That set ratio of atoms is the formula. That's what the formula of the compound tells you. So H2O means there's 2 hydrogen atoms per oxygen atom. That's the ratio of atoms, 2 to 1. That ratio of atoms gives the formula. The ratio of masses of those atoms to the sample mass gives the percent composition. So instead of talking about the ratio of atoms, it's the ratio of masses of those atoms. So here's how you do it. What happens is for each element in that compound, what you do is you take the number of atoms of that element in the formula, so as H2O, it would be 2 for hydrogen and 1 for oxygen, times the molar mass from that element. The molar mass from that element, you remember, you get from a periodic table. Just look it up on the periodic table. And you divide that by the mass of 1 mole of that compound. That's the molar mass of the compound, which we looked at in the earlier section. and then you convert that ratio into a percent by multiplying by 100%. So let's do an example. If you're going to do this, what you're really doing is you're taking the formula, and from the formula you're determining the percent composition. And it's independent of how much you have. Does not matter how big the sample is. And the reason is that you're looking at a ratio of something. So if it's like 30% one element, it's going to be 30% one element, whether you have a ton or whether you have a gram. Because of that, you can assume you have as much or as little of that compound as you like. And it's easiest to just assume you have 1 mole of that compound. That's the easiest way to do it. You don't have to, but it actually makes it a lot easier and makes a lot more sense. So let's figure out the weight percent of each element in N2O5. So what you do is you say you have 1 mole of N2O5. And what you want to do is you want to figure out the mass of the nitrogen in there. We'll do nitrogen first. And figure out the mass of the whole compound. So it's going to be 2 times the molar mass for nitrogen. You look that up on a periodic table, 14.01. So it's 2 times 14.01 grams per mole of nitrogen. And we're going to divide that by the molar mass of the compound. Now, the molar mass of the compound we have to calculate for N2O5. And now that you're done with section 3.1, I'll show you the easy way to do that. You just go to a website and do it there. So Google molar mass calculator. There's a bunch of them there. I use the one that comes up first. Type in N2O5, and you get the molar mass of 108.01. When you go to one of these, do a couple by hand to check it out, to make sure it works. But then when you trust it, you're good. Okay, so it's that 2 times 14.01 divided by 108 times 100%. And that comes out to be, I might use my calculator, 28.02 divided by 108.01 comes out to 25.9% nitrogen. Now for oxygen, you could determine the percent oxygen just by subtracting that number from 100, because the 2 have to add up to 100, because you have 100% of your compound and there's only 2 elements. So it should be around 74.1%, but let's go ahead and do it out anyway. So for oxygen, you have 5 oxygens times the molar mass for oxygen. Oh, go to 15.999, so it's 16.00. Get back there. 16.00 grams per mole of oxygen, divided by the same molar mass for the compound, 108.01 grams per N2O5, times 100%. And if you do that, 5 times 16 equals that, divided by 108.01, 74.1%. So it's a good check to see when you're done if they all add up to 100%, and they do. That's it. Now, that's not what I wanted to do. Okay, now what we're going to do is we're going to go in the opposite direction. So in the one we just did, you took the formula and you determined percent composition. Now we're going to take the percent composition and we're going to determine the formula. In this case, it's easiest not to assume you have a mole, because you don't know what a mole is, because you don't know the formula. So that doesn't make much sense in trying to do that. Instead, what you do is you assume you have 100 grams, and we'll see in a minute why that matters. Actually, we'll see right now. If you have 100 grams of your sample, for each element, you know the percent composition, that's the weight percent composition, so the mass present in a 100-gram sample is equal to the percent composition in grams. So if one element is 30% in terms of its weight percent, if you have a 100-gram sample, you have 30 grams, so you know that. So now you have grams of each element. You can convert those to moles for each element, and then you compare moles for each element to get the formula. And the reason that works, and this is really important, the ratio of the moles of the element, so the ratio of the moles of the element equals the ratio of the atoms in the formula, because those really reflect the same physical reality. So if you get the ratio of moles, you get the ratio of atoms in the formula, and therefore you get the formula. So let's go do an example. This is the example from your book. We have these percent composition values, And these are done by experiment, and you're going to be doing an experiment like this during class somewhere along the way, probably. And so you have these percent compositions that are measured by experiment, and they're weight percent. So you have a compound that contains potassium, sulfur, and oxygen in these percents. The first step is to convert those into grams, which means this will become 41 grams, this will become 33.7 grams, that's 25.22 grams. The next step is to convert those grams of those elements into moles. And you do that here. I'm not going to go through it and belabor it because you did a bunch of that. 41.09 grams times 1 mole over 39.098 is the molar mass for potassium. Let's go look at that. That's where that comes from there. And you do the same thing for sulfur and for oxygen. So you convert those into moles. So you have the moles for each of those elements. And then here's the key. What you do is you want to find the ratio of these moles of these elements. And so what you do is you divide the larger ones by the smallest one. And so you take the smallest one, which is actually either of these two, it doesn't matter. And you take the moles of each of these that you got for each element, divided by the smallest one, and that gives you the relative number of moles of each of those elements. So you have, in your formula, you have 1 mole of potassium, 1 mole of sulfur, and 1.5 moles of oxygen. From that, you get the formula. And here's the idea. What you have is you have a formula that is initially KSO 1.5. And remember, there's a 1 here and a 1 here. So what this 1.5 means is that you have 1.5 oxygens per sulfur. And so what you do is that means you convert that into a fraction, so it's 1.5 oxygens per sulfur, which is the same thing as 3/2 oxygens per sulfur, which means you have 3 oxygens for every 2 sulfurs. And so the formula then, and the same thing is for potassium, so the formula then would be K2S2O3. That's how you get a formula from that. And so notice part of this was that we took our 1.5 and we converted that into a fraction, 1.5. What other fractions are important? So let's look at, there's a big table here for you. So this is actually somewhat repeating, you'll see in a second. And it's based on a few important decimal to fraction conversions. And so the one we saw is this one here. 1.5 is 1.5, which is 3/2, which gives you the formula A2B3. If you had 1.25, for example, that's 1 1/4, which is the same as 5/4, which means you'd have 4 of one atom and 5 of the other atom. If you had 1.33, you'd have 1 1/3, that's 4/3, which means you'd have 4 of one atom and 3 of the other atom, and so on. So the thirds of the 1.33 to 1.67 gives you 1 2/3, goes to 5/3, which goes to A3B5. So these are just some other ones of those you can use. Now we turn to the idea of molecular formulas as opposed to empirical formulas. Empirical formulas is the kind of what you would get if you did an experiment, just figure out how much of each element was there. It's empirical because it's by experiment. The actual molecule may not have those numbers of atoms in it, but the ratio would be the same. So let's look at 2 examples here. Here's an organic compound called cyclopropane. The molecular formula is very clearly C3H6. The empirical formula is CH2, because that's the ratio of the atoms. For cyclobutane, a similar compound, the ratio of the atoms is, the molecular formula is C4H8, just counting up the atoms around there. The empirical formula there is also CH2. So these 2 compounds, they're different compounds, they have different boiling points, different melting points, different properties. They have different properties, they're different things, but they have the same empirical formula. So that's the difference between an empirical formula and a molecular formula. The molecular formula is always a multiple of the empirical formula. That multiple might be what? It might be equal to the empirical formula, but it's either equal to the empirical formula or twice it or 3 times it or 4 times it, etc. Okay, so if you know the empirical formula, how do you find the molecular formula? The answer is you use the molar masses of the 2. You compare the molar mass of the empirical formula and the molar mass of the molecular formula. That gets you how many units of the empirical formula is in the molecular formula. So in this case, it would be 3 units because there are 3 CH2 units there, and this would be 4 units because there are 4 CH2 units there. Okay, so let's look at this example we have here, and let's erase some of the stuff I wrote in the way. Clever lad that I am. So in this case, if we look at the one on the right, what we have is a molar mass is CH2. The molar mass of the empirical formula, that is CH2, you just calculate that. CH2 has a molar mass of 14.03. If the molar mass of the compound is measured to be 56.11, that's in grams per mole, what you do is you divide those two, and you see that 56.11 grams per mole divided by the molar mass of the empirical formula gives you 4, which means the molecular formula is equal to CH2 4 times, which is C4H8. So what you do is you get the molecular molar mass of the compound and compare that to the molar mass of the empirical formula. The molar mass of the empirical formula you just calculate from the empirical formula that you figured out. The molar mass of the compound you do by experiment, and it's done by mass spectrometry, which is the same experiment we use to determine which isotopes exist. Okay, so let's look at an example for this and also how to do it. To figure out the molecular formula for a compound, what you do is use the percent composition data. That gives you the empirical formula. We did that a couple minutes ago. You combine the empirical formula with the molar mass for the compound, which is done by mass spectrometry, by an experiment, and that gives you the molecular formula. So the process is, for each element, mass percent equals the percent composition in grams. Convert grams to moles for each element. Compare those to get the empirical formula. So we did this already. That's what we did to get the empirical formula. And then the final step is compare the empirical formula molar mass to the compound molar mass to get how many number of units, to get the number of empirical formula units. All right, let's look at an example. You have a compound that's made of carbon, hydrogen, and oxygen. You know these are the percent compositions. That's done by an experiment. You know the compound has a molar mass of 110.11 grams per mole, and your goal is to figure out the molecular formula. So the first step is to get the empirical formula. And so you take each of these percents, use them as grams. You're doing that by assuming you have 100 grams of that sample, which is perfectly fine. You divide each of those masses for each element by its molar mass, the elemental molar mass. These are from the periodic table. That gives you a relative number of moles of each of those elements. You then find the empirical formula by dividing the moles of the larger ones present to the lowest number of moles present, which in this case is that for oxygen. And so when you do that, you take the moles of carbon divided by the moles of the smallest moles present. You get 3 moles of carbon, 3 moles of hydrogen, and because oxygen is the smallest, it comes out to 1 mole. So the empirical formula, no fancy-dancy fractions this time, it's C3H3O, because they're all integers. Now let's figure out the molecular formula. The empirical formula has a molar mass. Take the molar mass of that, it has a molar mass of 55.06 grams per mole. What you do is you compare the molar mass of the compound, 110.11, that's from the experiment, that's the empirical formula molar mass, that gives you a 2. That means there are 2 of these units in the molecular formula. So the molecular formula is equal to C6H6O2. You double everything. If this number had been a 5, you would have taken all of these things and multiplied by 5. We finally come to our last topic, and that's hydrated compounds. Hydrated compounds are a special form of compounds. They're, I think, always ionic compounds, and they have bound water molecules. And it's important to realize that the water molecules here are not just dampness or wetness. These water molecules are part of the molecular or ionic structure of the compound. And in fact, what happens is the water molecules most often bind to the metal. So in this compound here, the copper ion has a 2+ charge there. We'll have the water molecules will be forming a bond to the copper as part of that structure. So the water molecules are part of the structure. There's lots of important compounds that you use. Gypsum, which is used in walls. Epsom salt, which is used for sucking stuff out of sores and for other things. Back when people used film for photography, sodium thiosulfate pentahydrate was used. Some people still do. Plaster of Paris, and I have no idea what blue vitriol does, but it is in fact a root killer. Okay, the question we have is, how do you determine the numbers of waters of hydration for one of these compounds? So let me go back for a second. How do we know that's a 5? And how do we know that's a 7? And how do we know that's a 5? And how do we know that's a 10? How do we determine that? And the answer is, what you do is you heat off the water. You heat up the compound. You burn off the water. It's not really burning, but it's evaporating off the water. You force the water out of the compound and see how much the mass decreases. And the idea is that mass loss, that loss in water, will give you grams of water lost. And that grams of water lost you can convert to moles of water. When you've gotten rid of the water, you've got this compound left that no longer has water. That's called the anhydrous compound. That anhydrous compound, the one that no longer has the water on it, is the root compound, and you know now how much it weighs because it's the mass of your final thing when the water's gone. So you have the moles of the anhydrous compound, and you divide those two, and that gives you the numbers of water's hydration, because it's the moles of water divided by the moles of the anhydrous compound. So the idea is, if you had copper sulfate, and in this case you had 5 waters, what happens is you heat it. A little delta symbol above a reaction arrow in chemistry means heating it. That will give you copper sulfate anhydrous plus the 5 waters. And the idea is the mass decreases of your solid because the water has left. And so that mass decreases, that equals the grams of water. So the grams of water will give you the moles of water. The grams of the anhydrous compound gives you the moles of copper sulfate, and then from that you can determine the number of water molecules.